Okay, now let's solve some other examples on the flexibility method for the statically indeterminate frames. We already solved the example number 1 in very detail. So in example problem number 2, we will be going a little faster, okay, because already we solved everything in detail in the problem number 1. So now let's quickly look at the problem number 2. Now we are given with 3 frame members. This is the frame member number 1, this is the frame member number 2, and this is the frame member number 3. The heights of the member number 1 and member number 3 are 15 feet, whereas the length of the member number 2 is equal to 30 feet. The external loads acting on the structure are the same as we discussed in the problem number 1, and they are 5 kip point load at this joint B and a uniformly distributed load of magnitude 2 kip per foot. Okay, and we are asked to analyze this frame using flexibility method. So what was our step number 1? Step number 1 was to find the static indeterminacy, because by finding the static indeterminacy, we come to know that how many extra unknowns we have which cannot be solved using the available equilibrium equations. So the static indeterminacy can be determined by 3b plus r minus 3n. We know that b is the number of frame members. In this case, we have 3 frame members. R is the number of support reactions. So we have 5 support reactions here. Now 3 support reactions at this support A and 2 support reactions at this support B. So total support reactions are 5. The number of joints are 4, A, B, C, and D. These are the 4 joints we are counting. And if we plug in all these values in this equation, so we come to know that the static indeterminacy is equal to 2 degrees. Okay. Now, what we do in the step number 2, that we select the redundants, and release them to obtain the basic determinate structure. Okay, so now the 2 redundants, we can select from this support A, we can select from this support B. I have selected it at this support D, so I will release the reactions at this point. When I release this support, I will then show my redundant actions. Okay, so this is my first redundant action pointing upward, and this is my second redundant action, which is pointing in the rightward direction horizontally. Now, what are the values of this AR1 and AR2? Both are unknown, and we will be using the flexibility method to find out the values of AR1 and AR2. So once these values will be known to us, the whole structure then can be analyzed by using the available equilibrium equations, because these are the only 2 unknowns which cannot be solved using the available equilibrium equations. So this is the redundant action matrix. Now next is the DRS matrix, and we know that DRS matrix corresponds to the support settlement or support rotation corresponding to the chosen redundant actions. So we have chosen these 2 redundant actions. Now, is there given any support settlement or rotation corresponding to these 2? So there is no support settlement, there is no support displacement corresponding to these 2 redundant actions. So our DRS1 value is equal to 0, and our DRS2 value is also equal to 0. Okay. So now we will obtain our basic determinant structure by removing the applied external loads and also by releasing this joint at point B. So this is now our basic determinant structure, BDS, which we will be analyzing now in step number 3 here. Okay, in step number 3, we will be analyzing the BDS when acted upon by the external loads. This is the first part of the first sub-part of the step 3. And from this step, we will obtain the capital M values. Now we know that what are the capital M values. The capital M values will correspond to the bending moment equations for each member due to the externally applied load. So now this is the now let's start with the member number 3. So if you look at this member, we don't have any external load applied on this member. So the axial load, the axial force, the shear force, the bending moment at this point B, as well as at this point C, they will be 0 because there is no external load acting on this member. Okay. Now, if you write the bending moment equation for this section A, for this cross section. So now there is no load acting and there is no force which causes moment about this section. So the moment equation will be 0. Okay. Now in same way, now if you look at the next member, now we have external load applied here. This is the 2 kip per foot uniformly distributed load. Now this load will cause shear as well as moment, and both the shear and moment will be resisted at B. Okay, because now we are carrying our analysis towards this one, and if we take the resistance on this one, now that resistance will be transferred over here, and then we know that there is no support. Resistances cannot be then supported by this joint B. That's why we don't want this joint to resist shear or moment or axial force. Okay, so all the shear and the bending moment will be supported at this joint B. Now, similarly, for this member, now these moments and shears and the axial forces, now they will be transferred to this member. So the shear force now will be acting as an axial force for this member. Okay, and if we solve out, so we will find out that using the available equilibrium equations we discussed in detail in problem number 1. So we come out with these values of axial force, shear force, and bending moment at this joint A. Okay, so now if we go back to the bending moment equations, so the bending moment equation for this member is equal to 0. For this member, it is equal to negative x square, y negative x square. This is exactly the same as problem number 1 we solved, right? So we have taken a section at this distance x from the C, origin C. And now at this section, we want to find the moment equation. And the moment will be coming from this 2 kip per foot magnitude uniformly distributed load. So if you multiply this 2 kip per foot with this x, and then again multiply with the x by 2, this will give you negative x squared. And the negative sign is because of our sign convention we already discussed. Okay, so if we come to this member, now the bending moment equation will look like this. Okay, so these m values we will be writing then in the table from this slide. Okay, these are the m values which we will be using in the equation later on. Okay, now in the second substep of the number 3, we now are looking for the M1 values, small M1 values. And from where they will be coming? They will be coming from the BDS when acted upon by a unit load. And that unit load should be acting corresponding to the redundant location number 1. Okay. So what was redundant location number 1? It was this upward unknown reaction. Okay. So now if you apply 1 kip load here, this 1 kip load will be resisted at this point, and accordingly it will be transferred at this point, and then it will be resisted here, and then it will also cause a moment at this, which will be resisted at this B. And similarly, this 1 kip and this 30 kip fit moment, they will be now transferred to this member, and finally they will be resisted at this joint A. Now, if you look at here, there is no other force which causes moment. The only moment we have here is the one which we transferred from this member CB. Okay, so these are the bending moment equations. This is the bending moment equation for this member. This is the bending moment equation for this member, and this is the bending moment equation for this member. Okay. So now, if you look at the next step, we will have now to analyze this BDS for a unit load which acts corresponding to redundant location number 2. Okay. So what was our redundant location number 2? It was this horizontally unknown force. So if we apply 1 kip load now in this direction, now this 1 kip, this will cause shear, and this will be resisted by this shear resistance at this point, C. Okay, and now the same shear will now be shifted to this member, and now it will be acting as an axial load for this member. Okay, and it will be then resisted at this point B, and when shifted to this member, now it will be again acting as a shear force. So this now will be causing a moment at this point A. Also, we have shifted this moment from this member. So now if you see, this 1 kip force is causing a couple. Okay, it is causing a couple. This 1 kip and this 1 kip. It is causing a couple. So this couple cancels out this applied moment because they have opposite sense. So this couple will cancel out this 15 kip fit moment. So as a result, we have 0 net moment at this point A. Okay. So if you look at the bending moment equations, this member, this is for this member, and this is for this member. Now we know that how these bending moment equations are obtained. Okay. So we have discussed them in quite detail in the problem number 1. So now, in the next step, now we have to arrange all these bending moment equations in the form of a table. Now, why we do this? We do this because we want our work to be efficient. And by efficient, we mean that there should be less chances of error, and we should go with our work a little faster. Okay. So this is the origin for AB. Now these values will be corresponding to member AB. All these values are corresponding to member BC, and all these values are corresponding to member CD. So the origin, we know these are the points which we have taken for writing the bending moment equations, and these are the limits which are from 0 to the length of the member. Moment of inertia, we know that for the first member it is equal to I, for the second member it is 2 times the I, and for the third member it is equal to I. And now these are the equations we obtained from the step number 3A or 3.1. Okay, when external load was applied. So this was the bending moment equation for the member number 1. This was for member number 2, and this was for member number 3. Similarly, the M1 values and M2 values, now these are given here. And they are coming from the step number 3B and 3C respectively. Okay. Okay, now these values we will now be utilizing in the next step for finding out the DRL matrix. And DRL matrix is corresponding to the displacement at a redundant location, okay? Displacement at redundant location due to external load acting on the BDS, basic determinant structure, okay? So we know that this M is coming from this row of the table, and the M1 is coming from this row of this table, right? So for the member number 1, you have to pick from this row. For the member number 1, you have to pick from this column. For the next member, you have to pick from this column, and for the third member, you have to pick from this column. So these are the capital M values. Similarly, the M1 values and the M1 values, which are only required here, so they can be also picked from this row. So if you plug them in this equation, you get your DRL1 to be equal to this one. Okay. Now, similarly, we can find out the DRL2. And what is DRL2? DRL2 will be the displacement corresponding to redundant location number 2 due to the external load applied. So now here we will be using the M2 value, and this M2 value will be coming from this row. Okay. For the first member, for the second member, and for the third member. So you apply this term on each member, and then you sum them as we have done here, and then you by summing you get this value for the DRL2. So this is the DRL1 value, this is the DRL2 value. So this is our DRL matrix. This is the DRL matrix which is required in step number 5. Okay. So now in the next step, we need to find the flexibility matrix, flexibility coefficient matrix. So we know that the flexibility coefficient value is corresponding to the displacement at one redundant location when a unit load is applied at any one of the redundant locations. So now in this case, we are finding the displacement at redundant location number 1, and we have applied the unit load also at redundant location number 1. So the formula is this one. This is the equation. So now we will be using both times the small m1 from this table, and then we sum them in order to get this value. Okay. Similarly, we obtain our F22 and in F22, and then we can also calculate the F12, which will be same as F21. So again, now F1, this one is corresponding to that we are finding the displacement at redundant location 1, and the unit load is applied at redundant location number 2. Okay, so we will now be using both M1 and M2. Okay, so now if you solve this, you obtain this value for F12 and F21. Why now they are same, F12 and F21? Because if you write M1 first or M2 first, it doesn't do not affect the final output, right? And the final output will be the same as this given here, 6750 divided by PI. Okay. So now this is the flexibility coefficient matrix. So now in the next step, let's find out the unknown redundant actions by this equation. So now this matrix is corresponding to the flexibility coefficient matrix, and this DRS1 value and DRS2 value, we know they are the support settlement rotation. In this case, they are 0. And the DRL1 and DRL2, these are the displacements corresponding to the redundant locations 1 and 2 due to the externally applied load. So when we plug in the values of the matrices we obtained in the previous steps, so we come up with the value of AR1 to be equal to 32.05 kicks and AR2 to be equal to -7. So now this -7 is, this negative sign is showing that the sign or the direction, actually, the direction of our AR2, which we have chosen to be acting in this direction, now it needs to be reversed, and we need to apply it in this direction. Okay, so we simply need to change the direction of this redundant action, which was AR2. Initially, it was acting in this direction. We have assumed that it is acting in this direction, but now our final answer is showing us that this direction needs to be reversed. So we now should apply it in this direction. Okay. Okay, so this was about finding the values of the redundant actions. So I have told you earlier that once the values of the redundant actions are known, then we can solve the remaining structure by the equilibrium equations. But if you are using this flexibility method, so there is a proper mechanism for this, and you have to use this. Let's look at this slide first. Here, now you can see now that this is the AR1, which is acting upward. And now if you see the AR2, we have now reversed the direction of the AR2. So initially we assumed it to be acting in this direction, but now we have applied it in the opposite direction. So this is now the final values of AR1 and AR2. Now we can apply this equation in order to find the member end actions for each member. Okay, what is this AM matrix? This AM matrix is the member end actions. Now this AM1 acting upward, this is our AM1. We have chosen this to be our AM1 for this member. This shear is the AM2, this moment is the AM3, and similarly the AM4 and AM5, this one, and AM6. So now we need to apply this equation for this member in order to find out these values of AM1 to AM6. So now what are the different matrices? First one is the AML, and now AML are the member end actions when the structure was subjected to the external load. Okay, so when we subjected the structure to external load, that was in the step number 3A. So we obtained these member end actions for this member AB, right? So now we simply need to write these values according to our proposed directions. So we have chosen our AML1 to be acting upward. So in this member, we have also this acting upward. So this will be taken as positive 60. Now we have chosen our AML2 to be acting in the rightward direction. But here, if we see, the shear at this point is acting leftward. So now we need to write this with the opposite sign, which is negative sign. Okay. Similarly, our AML3, we have assumed it to be acting clockwise. But if you look at this moment, it is acting anti-clockwise. So we need also to write it with the negative sign. Okay. And similarly, we can write all these three values. The AML4 is, we have assumed it to be acting upward, but it is acting downward, so negative sign. AML5, we have assumed it to be acting rightward. It is acting rightward, so positive sign. And we have assumed our AML6 to be clockwise, and it is also clockwise here. So we will take it as 900 positive. Okay. So this is our AML matrix. Similarly, we find out our AMR matrix, but these member end actions are now coming from the step number 3B, when we applied a unit load corresponding to redundant location number 1, and we analyzed the whole structure. So these member end actions are coming now from that analysis, and the method of writing them in the matrix are the same as we discussed on the previous slide. MR11, we have chosen it to be acting upward, but if you see here, this is acting downward, this force. So we will show it with a negative sign. And similarly, we can write the remaining values. After writing this one column, now we need to move to the step number 3, part C. And in part C, what we did, we applied a unit load at redundant location number 2. and we solved all the structure for that. So these are the member interactions we have obtained from that step 3, part C. And now the method of writing is exactly the same as we did on the previous slides. So why this is 0? Because this is 0, and this is corresponding to the AMR12. Why this is -1? Because our AMR22 is supposed to be positive in this direction, but the value we have, the member interaction we have in this member is acting opposite. So we will be showing it with negative sign. So in the same way, we can fill the remaining values, and this way we obtain the AMR matrix. So if we plug in these values of the AML matrix and AMR matrix and the AR matrix, okay, and the AR matrix. So if we solve this, we find out these values of the member interaction. So now this is the value of the member interaction 1. This is the value of member interaction 2, AM2. Similarly, AM3, AM4. So now if you see a negative sign, it will mean that the direction which we have supposed for our member interaction, now that needs to be reversed, okay? You simply need to reverse that direction. The value will remain the same. So similarly, these are the values of the AM4, AM5, and AM6, okay? Okay, so this is actually our axial force. This is actually our shear force at the lower joint of the member 1, and this is actually the bending moment at that joint, okay? Now similarly, this is the axial force at the upper joint. This is the shear force at the upper joint, and this is the bending moment at the upper joint of the member number 1, okay? So now next we write the shear force and bending moment diagrams. I hope there is this is clear to you, this shear force and bending moment diagram. You know from your mechanics. So let's move to the next member. Similarly, now for the next member, we need to find out the values of the AM matrix, and these values can be obtained by writing the AML matrix first, which corresponds to the member interactions when external load was applied on our structure, okay? Similarly, we need to write our AMR matrix. The first column is coming from the step number 3, part B, when we applied a unit load and we analyzed the whole structure for that unit load corresponding to redundant location number 1. And this column is coming from the step number 3, part C, when we applied a unit load corresponding to redundant location number 2, and then we solved the whole structure for that load. So we got these member interactions. So if we write them here, so we get this AMR matrix. So similarly, if we plug those matrices in the equation, so we get our values of AM matrix. This is the AM1 for the second member. This is the AM2 for the second member. Similarly, 3, 4, 5, and 6. Okay. Again, the negative sign will simply show that we need to reverse the direction of our member interaction. Okay. Now, the shear force and bending moment diagram here for the next member. Now we come to the member number 3, and in the same way we find out the AML matrix, the AMR matrix. Okay. And after finding the AMR matrix, we need to plug those values of AML matrix, AMR matrix, and AR matrix here, so that we can obtain the values of our AM1 to AM6 for the member number 3. So these are the values of the member interactions for member number 3. So again, we draw this shear force and bending moment diagram now for the member number 3. So the combined shear force and bending moment diagram for the whole structure now, you can see it. This is member number 1, this is member number 2, this is member number 3. And same way, this is the bending moment diagram for each member. Okay. So this was about the example problem number 2. We did it a little faster because we already solved it in very detail actually in the problem number 1. Now let's move to another problem, and this time we will be taking exactly the same problem number 2, but now in the problem number 2 we will be doing some changes. And what are those changes? We now are applying some translation at this joint D. So the joint D is translating by 0.5 inches. You can see this, that this joint is translating by 0.5 inches in this direction. Also, it settles down by an amount of 0.75 inches. So you can see that this support is also settling by 0.75 inches. It is given here. Now, how to solve now this structure? This is exactly the problem number 2 as we discussed. But now we have to incorporate these this settlement and this translation into our calculations. So let's see how we do this. The step number 1 is exactly the same. We have to find the static indeterminacy, and it comes out to be 2 degrees. This translation, this rotation, sorry, this settlement, it will not affect the static indeterminacy for sure. And now we are also given that the value of this modulus of elasticity and the moment of inertia we are given here for this structure. So if we multiply them, so we come up with this value. So now whenever we use the EI value, we have now to put the value of EI equal to this 125,000 Kip-Fitts square. Okay. So now let's move to step number 2. Step number 2, we release our joint, our support at joint D, and we write our redundant actions corresponding to the constraints we have released. This is AR1, this is AR2, and of course we have to find the values of this AR1 and AR2 through this flexibility method. Now, important to look here is that what are the values of DRS1 and DRS2. Now, DRS1 is corresponding to the redundant action number 1. Our redundant action, we have chosen our redundant action to be acting upward, and there is a support settlement corresponding to this redundant action, but that settlement is downward. This support is coming downward. It is corresponding to this redundant action, but it has an opposite direction. So we will write this with corresponding to the AR1, we will write our DRS1 value, but we will put a negative sign with this. Now, if we have chosen our AR1 value to be acting downward, for example, if we have chosen our AR1 value to be acting downward, then there would have been no need of writing this negative sign with this, because the settlement would have been in the same direction as our chosen direction for the redundant action number 1. Okay. So now in this case, in this actual case now, as we have chosen our redundant action to be acting upward, but the settlement is opposite to this and it is downward, so we need to write the negative value, this negative sign with this value of settlement. Okay. Now, if you look at the translation, so there, this joint also translates by an amount of 0.5 inches in this direction. So in this direction, we have our AR2. So we will write this translation corresponding to AR2 here. This will be our DRS2. Okay, and this is positive 0.5 inches because the translation is exactly in the same direction as the direction of our chosen redundant action number 2. If the translation was in this direction, then we need to write a negative sign with this. But as in this case, the directions of both the AR2 and the translation are the same, so we will need to write a positive sign with the translation. So this is the translation, and this is the settlement. This is our DRS matrix. Now we have converted it into feet because we are using feet unit for length most of the times in this problem. That's why we need now to convert this to feet for unit consistency. Now, from this step, we have obtained our DRS matrix. So now we need to apply the other step. In step number 3, we have to again now analyze the structure for the external load applied. So we have analyzed here. The procedure is exactly the same as we discussed in problem number 1 and 2. Okay, so these are the member interactions we have obtained. Okay, and these are the bending moment equations for member 1, 2, and this 3, or 1, 2, and 3. Okay, so these values now, these bending moment equation values now, they will be the M values, capital M values. Similarly, we write the M1 values corresponding to indication number 1. We have applied a unit load of 1 kip, and we have solved all these members. Okay, and similarly, in the next step, we have applied a unit load corresponding to indication number 2, and again we have solved the members. Okay, and we have also wrote these bending moment equations for each member. Step number 4, again we now develop this table, and in step number 5 we need now to find the DRL1 value, which will be the displacement at redundant location number 1 due to external load applied. So these capital M and this small m1 values are now, we are picking them from this table for member number 1, 2, and 3. Also for member number 1, 2, and 3, these are the small m1 values. We come up with our DRL1 value to be equal to this one. Similarly, we come up with our DRL2 value by taking the same values from the table on this slide. Okay, this slide we will now be similarly as we did in the previous problems. We will be using these values. So this is our DRL2 and this is our DRL matrix. Now we need to apply the value of EI. Okay, we now need to incorporate the value of EI. So this is the EI value which we have discussed on this slide, on the very first slide of this problem number 3. So if you divide this value by this, you get this value, and if you divide this value by this, you get this value. Okay, so this is the DRL1 value. Now there is no need to write the EI because we have incorporated the EI into our calculations. This is now the actual displacement by incorporating the values of EI. Okay, so now similarly we find out this flexibility coefficient matrix, which is of course the displacement at a redundant location due to a unit load applied at any of the redundant locations. So this is F11, which is the displacement at 1 due to unit load applied at 1. So we find out this value to be exactly the same as we did earlier. So F11, we can also find the F22. We can find this F12 here also. Okay. So if we find out this final flexibility coefficient matrix, so this is now we need to incorporate these values of EI. So if you divide each element of this matrix by this EI value, you come up with this value for your first element, and similarly these values for the other elements. of the matrix. So now this is your final flexibility coefficient matrix. Now we need to plug in these matrices in this equation. We have our flexibility matrix. We have our now DRS1 and DRS2 values. We have our DRL1, DRL2 values. So now if you plug them, you have to take care of the sign. We have negative sign with this, and also we have negative sign in the equation. So you need to take care of every sign here, right? So now DRS1, we know it is coming from that step where we calculated the that support settlement and that translation, and we wrote that corresponding to this redundant location 1 and 2. Okay, so this is the DRS matrix, this is the DRL matrix. When you apply these matrix, now this inverse and this, then you multiply them, you get this AR1 to be equal to 30.62 and AR2 to be equal to this negative 5.32. Okay, this EI will not cancel out because we have consumed the value of EI in this DRL matrix, also in the flexibility. So I think there is this EI should be cancelled. There is no need now to write this EI because it is already consumed. Okay, this is by mistake. I will remove this now. So now this AR1 is 30.62, AR2 is this negative 5.32. And again, the negative sign is showing that we need to reverse the direction of our redundant action number 2. Okay, so here we go. We reverse the direction of that. So we need to find out the member end actions, and the procedure is exactly the same as we discussed in the problem number 1 and problem number 2. So we need to find the AML matrix. The AML matrix is coming from when we applied the external load on the structure and we obtained the member end actions. Okay, so now that was in the step number 3A. Similarly, you find the AMR matrix. The AMR matrix is coming from the step number, this first column is coming from step number 3B, and the second column is coming from step number 3C. In step number 3B, we applied a unit load at redundant location number 1 and solved the structure. Similarly, for this, in the step number 3C, we applied a unit load at redundant location number 2 and we solved the structure. Okay, so once we obtain these matrices, we now need to plug in the values here, and so that we can get our final values of AM1, AM2, 3, 4, 5, and AM6 for the member number 1. Okay, similarly, now you draw the shear force and bending moment diagram for this member, and you go to the next member and you solve it for the AML, you solve it for the AMR. Okay, and you solve it for the AMR, and then you solve it for the AM by plugging the values of AML and AMR and AR here. So we get these values of the member end actions for the member number 2. So you do it again, and now you do the shear force and draw this shear force and bending moment diagram here, and then you go to the to find the member end actions for the member number 3. So again, we need to find out the values of the AML matrix here. They are 0. Why they are 0? Because due to external load, there was no shear, there was no axial, there was no bending moment. Okay, because there was no external load acting on this member. So that's why AML matrix is 0 here. So now you need to find out the values of the AMR matrix. Okay, and when you plug in these values, AML, AMR, and AR, so you get these values for the member end actions for the member number 3. So now we draw the shear force and bending moment diagram for the member number 3 also, and we then draw the combined shear force and bending moment diagram for the whole structure, which will look like this for the shear force and look like this for the bending moment. Okay, so this was all about the lecture number 3. Okay, now we will be starting our lecture number 4, which is about the uh, analysis of trusses, and the trusses are statically indeterminate. So now let's shift to the lecture number 4.